Okay, as we start week 4 here in Calc 1, we have two more sections to cover in Chapter 3 on differentiation. And both of these are really two separate but very important applications of derivatives, really. In section 3.8, we're going to talk about related rates. Related rates problems are the problem of finding a rate of change from other known rates of change, essentially, is what's going on. And we know that rates of change mathematically are derivatives now. So I'm going to just kind of start with an example, and then I'll walk you through the strategy for that and be very careful and precise as I walk you through the strategy in this example. The first example is example 47. So water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? That means exactly at the moment when the water is 6 feet deep. Of course, you're running water into this conical tank. It's only 6 feet deep at one instant in time. So what we need, this is a related rates problem. You'll eventually hopefully be able to identify related rates problems pretty quickly. But the strategy for solving these is the first step is to draw a picture and name the variables and constants using t for time, typically. Assume that all variables are differentiable functions of t. Assume that all variables are differentiable functions of t, right? Because as things change, they change with time. Step 2, we want to write down the numerical information in terms of the symbols we have chosen. Step 3, write down what you are asked to find, usually a rate expressed as a derivative. Step 4, write an equation that relates the variables. Sometimes you might have to combine two or more equations to get a single equation that relates the variable whose rate you want the variables, whose rate you know, okay? Differentiate with respect to t at that point. This is usually implicit differentiation because we're assuming that our variables are functions of t. And then evaluate using known values to find the unknown rate. Okay, so that's probably a little bit of a blur, so it's easy to kind of best go through this example. So remember the example, water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So the first step is to draw yourself a picture. And by the way, usually steps 1, 2, and 3 are kind of all done together. Okay, so we draw ourselves a picture and we try to label the things that are changing. Notice that this base radius of 5 feet is constant. That's never going to change. So this r is really not a variable. It's just 5 feet, this distance here. However, the radius about where the water level is constantly changing as the water rises. This x, the radius of the water level, I'm calling it x, will change as it'll get larger as the water level rises. And of course, the depth of the water y will change as the water level rises. This h is really not a variable, I just called it h, but it's 10 feet. This is a constant 10, the height of it, and this is a constant 5, the radius. So what do we know? Well, we know that the volume, the amount of water in here that's changing is changing at a rate of 9 cubic feet per minute, right? The volume, the water that's coming in is coming in at a rate of 9 cubic feet per minute. What we really want to know is what is the rate that the height is changing exactly when y is 6 feet. Because if we go up here, remember the question, tank stands point down, has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising? That's how fast is the depth changing when the water is 6 feet deep. Okay, so we've got in this first thing, we drew our picture, we labeled the things that were changing, which were x and y, and then we write down what we know and what we want. We know that the volume, the water changing in the volume of water changing in the cone is 9 cubic feet per minute because that's how much water is coming in. And we want to know how is the water level changing? What is the rate that the water level, dy dt, the depth of the water, is changing when y is equal to 6 feet. Okay, so in step 4 now, we have to write an equation that relates the variables. This is usually the hard part, is you need to know and or look up relationships you're not familiar with. Like you need to know the volume of a cone here is 1/3 pi r squared h. Now I'm not going to ask you to like when it comes to a quiz or a homework assignment or exam, come up with new things than we've talked about in class. So in this case, you need to know the volume. The volume of a cone is 1/3 pi r squared h. Okay, so what does that make the volume of our water cone? Well, remember, the r is the radius that is changing, that we called x, and the height or the depth of the water we call y. Those are the things that are changing. So the volume of the water that's in that cone is always 1/3 pi. R squared is really x squared in our picture, and y is the h. So relationship between x and y from similar triangles. Now the reason I can't stop here is because I have volume as a function of two variables that are changing, x and y. So I need to have volume as a function of only one variable. So I need a relationship between the x and the y before I can go through and take my derivative like I'm comfortable with. Because I need volume as a function of only one of these guys. So I need a relationship between x and y. So I get that from similar triangles, right? If I go back to my picture, similar triangles is a technique that we use often. We can see I have this big triangle here, and I'm going to have a similar triangle, this smaller guy here. So in other words, the base x of the smaller triangle is to the base of the big triangle, 5, in the same proportion as the height of the smaller triangle, y, is to the height of the larger triangle, 10. So we use similar triangles. So in other words, x is to 5 as y is to 10. I can either solve for x or for y. It doesn't matter. In this case, I chose to solve for x. Just multiply both sides by 5. So x is 5/10y, which is 1/2 y. Plug that in for x now. So in other words, we have 1/3 pi x squared y is the volume. So I'm plugging 1/2 y in for x. So 1/3 pi x squared is 1/2 y quantity squared y. Simplify that. 1/2 squared is 1/4 times 1/3 is 1/12. So 1/12 pi, and then y squared times y is y cubed. So now I have volume as a function of just y that is changing, because I knew a relationship between x and y. And then the last two steps, I want to differentiate now this equation with respect to t, express the rate we want, which remember we wanted dy dt when we know dv dt. So I want to express the rate I want in terms of the rates and variables whose values I do know. Then we use those known values to find the unknown rate. So first of all, take this function, v equals 1/12 pi y cubed, differentiate both sides with respect to t. So dv dt equals 1/12 pi, those are just constants, put them in front. Then I have the derivative of y cubed with respect to t. So y is some unknown function of t, so I have to use implicit differentiation. So I first take the derivative of y cubed, thinking of y as an inside function. I have 3y squared, but now I have to take the derivative of the inside function y, and I don't know y, so I write it as dy dt. I don't know the function. So that equals 1/4 pi y squared dy dt after some simplification. Solving that algebraic equation, right? dv dt equals 1/4 pi y squared dy dt. Solving that for dy dt, multiply both sides by 4, divide both sides by pi y squared. I get dy dt equals 4/pi y squared times dv dt. So that's the relationship between the known rate of change and the unknown rate of change. And now I want to know, what is that unknown rate of change exactly at the moment in time when y itself is exactly equal to 6. So I want to find dy dt evaluated when y equals 6. So that's 4/pi times y was 6 squared times dv dt, which we know is 9, right? 9 cubic feet per minute. This comes out to be 1/pi. I know the units there would be feet per minute. So 1/pi is about 0.32 feet per minute. That's how the depth of the water is changing as the water level is rising. For 9 cubic feet of water per minute coming into that cone, the depth of that water is increasing by a rate of 0.32 feet per minute.